Hello, welcome back from spring break. So today we're gonna take off where we left off before break. And before break, the last thing you did was look at that simulation and take some notes on how gases moved. And the thing we noticed was that if the molecule was heavier, it was moving slower on average than if the molecule was lighter. So slow molecules move faster at the high temperature, or at the same temperature, than heavy molecules. Just like to have the same energy, a truck and a motorcycle wouldn't be moving the same speed. The motorcycle would have to move much faster than the truck. So there it is qualitatively. The heavier it is, the slower it moves. So today we're going to deal with it quantitatively and stick numbers with it. So we noticed the relationship was inverse. The heavier the molecule, the slower it moved. So that leaves us with a mathematical thing that's inverse, but it's not quite exactly inverse. And we'll explain why in a minute. So Graham's law describes that relationship as an inverse relationship. So it says the rate of effusion and diffusion is inversely proportional. So it's the inverse that we were looking for. But it's not to the inversely proportional to the molar mass, but to the square root of the molar mass. We never had that square root piece pop up before. So where does that come from? Well, here's where it comes from. It comes from the definition of kinetic energy. Okay? Kinetic energy is calculated as 1/2 mv squared, where m is the mass, and v, notice it's a little v is for the velocity of the particles. So we get this inverse relationship if we use this equation. And let me show you what I mean. So there's our relationships. So if two things are at the same temperature, the kinetic energy for the first one equals the kinetic energy for the second one. So that I could write, oops, let's go back. 1/2 m1 v1 squared equals 1/2 m2 v2 squared. Now I can cross out the 1/2s because they cancel out, multiply it through by 2. And now I'm going to gather two terms. I'm going to put all the masses on one side and all the velocities on the other. So I'm going to divide both sides by mass 2. So those cancel out. And divide both sides by velocity 1 squared. So that cancels out. And I'm left with m1 over m2 equals v2 squared over v1 squared. And now I simplify by taking the square root of both sides, and I get that v2 over v1 is equal to the square root of the mass of 1 over the square root of the mass of 2. So there we have the inversely proportional. See how it's inverse? It's flipped. The 1s and the 2s are flipped. And the square root comes because I take the square root to get velocities by themselves. So this says that the velocities are inversely proportional to the square root of the molar masses. So that is Graham's law in terms of velocity. So bigger molecules move slower at the same temperature by the square root. So that means 4 times as heavy, half as fast. 9 times as heavy, flip that, that's 1/9 to take the square root, you get 1/3 as fast. So that means bigger molecules are going to effuse and diffuse more slowly. And you've seen this if you ever looked at a helium balloon. When you get a helium balloon, it's full of pressure the first day, and it floats away. But then as it sits, the balloon gets smaller. And that's because in a balloon, what you have is latex, which is long, stringy fibers that cross each other. Okay? And there's little tiny holes there in between those fibers. And if a helium hits that hole, it gets to go out. This is the effusion through a small hole, going from high concentration to low concentration, which is what you learned last year. Helium's at high concentration inside the balloon and low on the outside of the balloon. So over time, that helium will escape. But you'll notice that the balloon never goes completely flat, because while helium is hitting from the inside trying to go out, the air is hitting on the outside, and if it hits the hole, it gets to go in. So oxygen and nitrogen are diffusing in, while hydrogen is diffusing out. So we got helium leaving the balloon, and oxygen and nitrogen entering the balloon. Now, helium's a lighter molecule, so it's going to escape faster than nitrogen and hydrogen are going to go in. So over time, your balloon gets smaller, but it never goes completely flat. But when you're done, the helium has left the balloon, and what's inside there is oxygen and nitrogen. Okay? And since oxygen and nitrogen is not less dense than air, because it is air, the balloon no longer floats once the oxygen and nitrogen goes in. So you've seen this happen. The balloon gets smaller because the helium leaves and the air comes in, but the air comes in slower than the helium leaves. Now, if you've ever gotten a Mylar balloon, just notice Mylar balloons the shiny metal ones stay full forever. And that's because they don't have these holes. Mylar is one continuous sheet without the holes, so they can't escape. The only place they can escape is through the hole in the bottom. So Mylar balloons don't go flat. So this is Granville's laws and equation. The rate of effusion of 1 compared to the rate of fusion 2 is equal to I'm using m for the molar mass, of 2 over 1, inverse square root. Okay? And that's because effusion is based on velocity. So we just did this thing. Because effusion depends on velocity, you get the same thing. And since diffusion, we could actually use the same equation for diffusion. Oops, I think there's only one F in diffusion. There's two F's. Okay. Now, effusion rate, and velocity are all rates, how fast they happen over time. Okay. Now let's see how time relates to mass. If you had a heavier molecule, it would escape slower, so it would take a longer time for it to diffuse. So the heavier it is, the slower it is. The lighter it is, the faster it is. The heavier it is, the longer time. Lighter, shorter, lighter, faster time. So as weight goes up, time goes up. So time and mass are directly related. So the bigger mass will take the longer time, so they're directly related. So time is the inverse of velocity, so time is directly related to mass. So let's try a few examples. These are the last 3 on your examples questions. So in a test, they let a helium effuse and it came out at 3.5 moles per minute. How fast would nitrogen effuse in the same conditions? So they gave me a rate. So I'm going to want to have the equation with rates. So rate of, I got 2 rates I got to compare. And the rate, I want the rate for nitrogen. So I'm going to put the rate for nitrogen on top because I like solving for things on top better than solving things on the bottom. It doesn't matter which one you choose. It just makes the math easier if you pick nitrogen for the top. Otherwise, you have to solve for something on the bottom. And that means it's going to be the molar mass of nitrogen on the bottom, inverse, and the molar mass of helium on top. Now, the molar masses I can get from the periodic table. So I know this number, and this number, so I can find the rate of N2. So the rate of N2 is going to equal the square root of the molar mass of helium over the square root of the molar mass of nitrogen times the rate for helium, which is the square root of 4 grams divided by the square root of 28.02 grams times 3.5 moles per minute. You notice the grams cancel out, leave me only units I want. And you push those buttons, you will get 1.3 moles per minute. Okay, now at the end of every one of these, check and make, if you make a mistake, it's going to be because you made it upside down. So let's check and make sure it changed the right direction. Okay, so nitrogen is heavier than helium, so nitrogen should effuse slower than helium. So I should get a smaller rate, and I did. I got a smaller rate. 1.3 is smaller than 3.5. So that's how you do these. Let's try the next one. So here they compared how fast they effused. So they said it's 2.82 times faster. That's a rate comparison. And they want to know the molar mass of the unknown gas. So they want to know the molar mass of the unknown gas. So I'm going to put the square root of the molar mass of the unknown over the square root of the molar mass of H2. And that's going to be inversely proportional to the rate of HE over the rate of, sorry, H2, sorry, it's not HE, it's H2. It's HE last chapter, of the rate of X. But we already know this answer. It says H2 effused 2.82 times faster. So this is 2.82, this part right here. The rate of hydrogen compared to the rate of X is 2.82. So now I just have to solve for the molar mass of X. So I get this, I get that the square root of molar mass of X is equal to 2.82 times the molar mass of H2, and H2 is 2.02 grams. So if I push those buttons, 2.82 times the square root of 2.02, gets me the molar mass of X is, with 3 sig figs, that's 4.01 grams. Okay? And looking at that, that means I got an unknown gas that weighs 4.01 grams for each mole, and the only gas that could be would be helium. This must be helium because its molar mass matches up with the molar mass of helium. So we can use this to identify gases. Okay. In this example, I give you a time, 89.3 seconds, another time, 60 seconds, and they want to know the molar mass of the gas. So I got the molar mass of X. I always put the thing I want on top. Divided by the molar mass of O2 is equal to, okay, so it's time. And we said time, I got 2 times, I got to compare the 2 times, and time was direct or inverse. Well, if it's heavier, it's going to move slower, so it's going to take more time. Heavier is more time, more mass is more time, so that makes it direct. And I have 3 of these numbers. I got the time for the unknown, I got the time for O2, and I know the molar mass of O2. So I can solve this so that the square root of the molar mass of X is equal to the time for an unknown gas was 89.3 seconds. The time for oxygen was 60 seconds. And the molar mass of O2, the square root O2 is 32.00 grams. So that gives me that the square root of the molar mass of X is 89.3 divided by 60 times the square root of 32. Gets me 8.41. And my units are grams to the half because I took the square root of grams down here. That's grams to the 1/2 power. But I got to square this anyway. The molar mass of X is equal to, now I square that, and I get 70.9 grams. And at 70.9 grams, this might be chlorine. So we can use these molar masses to help us identify unknown gases. In fact, this is where we can get the molar mass so that we can do problems where we take an empirical formula and turn it into a molecular formula. This is how they know. So, in summary, it's an inverse square root relationship. So to set up the equation, make sure you set up the relationship right. If it's inverse, set them up upside down. If you make a mistake, it's going to change the wrong direction. The homework is on the form. Make sure you show your work on your papers so that when I see your notebook, I'll be able to look for that. Have a great day. If you took the test, I took the quiz on Friday, before we left, the scores are up. If you missed the timing window, apparently there's a timing window, who knew? If you missed the time window on Friday, I will put up a retake tomorrow. I didn't realize that 2 o'clock in the afternoon was too early for you guys, but I'll change that to make the window open from 1 to 5, and I'll put that up tomorrow. Otherwise, have a great day. Stay safe. Be well.